So here we are talking about compound interest. Just a little brief summary of what we were on to. So effectively, we're looking at this topic just in terms of it. This is chapters 9 in the brand new book, or chapters 8 in previous editions. So I don't want anyone to get confused there. Compound interest is really used. It is the way that interest is normally calculated for most loans. Okay, so it is the common thing, and we really need to be familiar with it. Effectively, how it works is interest is charged on top of interest. And I've shown here in this little example that normally compounding occurs for longer lived loans, okay, loans over a year, for example. However, there's nothing to prevent a loan from having any length of loan being set up as a compound interest. But generally, they're for longer term loans. So if we were to take this example, if you had an amount of money, say $1,000, which is what we see here in the first instance, at time zero, you borrowed that, or you had it in the bank and you're earning interest on it, whatever, you're either a borrower or a lender, depending on your perspective. If it earns 10% interest, what happens in the first year, if the way the interest is set up, it's an annual interest rate of 10%, you will find you will have the $1,000 principal plus another $100, and that $100 is really the interest, 10% of $1,000. In the subsequent year that goes on, in year 2, for example, then that $100 interest gets added to the principal, so it becomes $1,100. And effectively, the interest is calculated based on the new principal. So it's interest on top of the interest. So the interest in the second year will be $110. And in the third year, likewise, that 1,000 plus the 100 plus another 110 comes to $1,210. And that interest is calculated on top of that for a total of $1,331. So compound interest is good if you are a saver. If you're loaning money, compound interest means that you're getting progressively more and more interest as time goes by. But if you're a borrower, compound interest is not your friend, because what it does is that interest compounds and you're paying interest on top of the interest, more or less, as time goes by. So the very first thing we talked about was this issue of, well, how in the heck do you calculate this anyway? So the first thing we needed to do was to understand how the basic calculation and how the process of the calculation takes place. The very first thing we need to do, seeing it is compounded and that we may have more than one compounds in a year, is to be able to think about something called the periodic interest rate. The periodic interest rate is the effective rate of interest that is charged in the compounding period. So what do you mean by a compounding period? It could be a month, it could be a week, it could be a day, it could be half a year. There are any number of compounding periods, and normally in any situation where we have loans, the contract of the loan will specify how the interest is calculated: daily, weekly, monthly, semi-annually, or just annually. In order to be able to calculate the periodic interest rate, what we do is we take what's called the nominal interest rate. Interest rates are always stated in nominal terms. In other words, that is the effective yearly rate of interest. So let's say, for example, the interest rate is 10% nominal, or the annual interest rate is 10%, and we have a semi-annual compounding, meaning there's 2 compounds a year. The effective or periodic interest rate then is really 10, which is the annual, divided by the 2 compounds per year, which is 5% per period. And we saw some examples of that here, where, for example, if we took 10.5% compounded annually, all we need to do is take 10.5 divided by 1, that's 10.5. If 9.5% is compounded quarterly, well, that's 4 times a year. We take the 9%, the annual rate, divided by 4, and we'll get 2.25 per quarter. And we can manipulate this same basic formula, this little formula that was brought in here, which is periodic interest rate is the nominal rate divided by the number of compounds per period. we can manipulate, we can find, given two, any two, I, J, or M, any two of those, we can calculate the third. So that's what we did in that very first section. We looked at that, and
Hello,
I
everyone.
have
It's Paul
explained
Tilley.
it
Thanks for
here
joining me
in
here
this
today.
in the video, and you could take a look at that. There was also some exercises there, and I have worked those out in the
Hello,
little
everyone. It's
video
Paul Tilley.
that goes after that. Plus, I have some of them written out here if you'd prefer that. Okay, whatever works for you. What we finished up on last week, or last class, was this issue of applying this basic concept. Okay, the first part dealt with, well, here is the basic concept. Now we're into the application of it. So how does this work for certain types of loans? So the very first thing we looked at was this issue of, well, okay, in any loan situation, if we got compounding on the go, we need to know how to calculate the future value or the present value, okay, of an amount of money. So what is $100 today going to grow to in 5 years, given a set of interest rates and compounding? Well, this is the basic formula here that is used for calculating the future value, which is going out and saying, okay, what will the value be in some future date? And it is a pretty straightforward formula. The future value is the present value multiplied by 1 plus the periodic interest rate to the power of n, which is the total number of compounds in the time period. Okay, and we saw an example of that, and that can be a little bit confusing. Now, you want to make sure that n is the total number of compounds in the length of the loan, not number per year. So we had a little simple application here. Assume you have $100 compounded quarterly, 4 times a year for 1 year. So what we have is really we have an annual interest rate of 8%. And what we need to do is to say, okay, well, the annual rate is 8%, 4 compounds per year. So that's 2% per period. That's the very first thing we need to do. We need to be able to say, what is the percent per period? And that will be our value I. And then we have to ask ourselves, well, how many compounds are there total in this loan? Well, it's 4 times a year, and it's 1 year loan, so that's 4. So n is 4. We just plug the numbers into the formula as I've done here, and we will get 108.24. In other words, if we put $100 in the bank at the beginning of the year, it grew at a rate of 8% compounded quarterly. At the end of the year, we would have 108.24. And we did a bunch of examples here, and there's a lot of good examples that show you how to do the basic problem. So what's the maturity value of $10,000 invested for 5 years at 3.5%, compounded semi-annually? So we got to get some takeaways from that. The present value is $10,000, for example, is the first takeaway. The other thing is we need to say, okay, what is the periodic interest rate? Well, it's 3.75%, but it's compounded semi-annually. Semi-annually means 2 times a year. So we got to take 3.75 divided by 2, and that will give us the I, which is the periodic interest rate, of 1.875%. We also know that it's 5 years, and as a semi-annual thing, so that's 5 years times 2 times a year, which is a total of 10. So n would be 10. We just throw the numbers in the formula, and we get the total value of the investment at the end of the 5-year period would be $12,041.38. And we did a couple more examples there where we're taking that basic concept and applying it to other scenarios. You know, if we're looking at, for example, comparing a couple of investments. So which is better, you know, an interest rate of X and a compounding of Y. And we look at 2 different ones, and we can, you know, figure out which one is the better. And that was what this example was about. And then we looked at the potential for the interest rate to change at some point during the loan. And what we do there in order to resolve those types of questions is we calculate the future value of the original interest rate. So the interest rate is in place for X period. In this particular instance, in this particular problem, the interest rate was 4.25% compounded quarterly for the first 18 months. The second 18 months was 4.75% compounded semi-annually. So all we need to do there is really figure out the future value to month 18. And then that future value of month 18 becomes the present value for months 18 through 36. And we just do the math on that, add the two numbers together, and we get the total value of the total. Okay, so that's what we looked at there. We can also find, if we're missing I'm going to say missing a payment or missing a balance, and we can figure out what the total amount is. So Faye borrowed $5,000 and interest rate 3% compounded quarterly. On the first, second, and third anniversaries of the loan, she made payments of $1,500. What payment made in the fourth anniversary will extinguish the debt? And so we see we can chase along here. For example, we can do the future value calculation to year one. We pay $1,500. That gives us a balance, which becomes the present value for year two. We do the math on that. We calculate the future value at the end of, or at year two, right here. We subtract $1,500 for that, and we do the same thing right through, and that will give us the future value there for the last one. Said, okay, let's look at some of these problems. Here we go. We'll take a look at number one. And we've done this before. Anyone who says, hey, this looks familiar, we have. I just want it, just in case someone wasn't here on Monday, and just to reinforce what we've done. So what is the maturity value of $5,000 invested at 3% compounded semi-annually for 7 years? So we've got some key information there. We know that the present value is $5,000. In other words, we start out with $5,000. We invest it at 3% compounded semi-annually. Semi-annual means twice a year. So what we got to do is take the 3%. In order to find the value of I, or the periodic interest rate there, we got to take this 3% and divide it by 2 because it's semi-annually. That would be 1.5% per compound. We also know that it goes on for 7 years. So it's a semi-annual compound for 7 years. So that's 2 compounds a year for 7 years. 2 times 7 is 14. So with that little, but here effectively is the problem resolved on paper. Okay, so as I say, the present value is 5, the nominal is 3, it's a semi-annual, and it's for 7 years. So what we need to be able to do over here, this is the formula that I've just thrown in here. So the present value is 5, the periodic interest rate is 3%, divided by 2 because it's semi-annually, as I say, 1.5% per period. The N, which is the total number of compounds, it's 7 years times 2 per year. That's where that comes from. So 14. So we just take these bits and we put them in this formula. So the present value is 5,000. 1 plus the I, which is 0.015. So that's 1.5% is 0.015 to the power of 14. We run that through our calculator. So that's 5,000 and 1.015 to the power of 14. So we do the math on 1.05 to the power of 14, multiply it by 5,000, and we'll get $6,158.77. So all this is saying to us is, look, if we put $5,000 in an investment that earns 3% annual rate of interest that compounds semi-annually, after 7 years, we'll have $6,158.77 there. Okay. Any questions?
How did you plug that into the calculator? I can't come up with the same answer.
Oh, great. Good point. Good point. Well, one of the things you have to concern yourself with is something called the order of operations. So we're going to do this part over here. Let me make sure you can see my cursor. We have to do this part over here. Oh, this part over here first. So if you were to take 1.015, this number right here, to the power of 14, so on your calculator, that will give me 1.2317557. And then I multiply that by 5,000. That'll give me 6,158.77. So the order of operations is a critical thing. You need to be able to do that first. I'm just going to look at the second one then. What's the future value of $8,500 after 5.5 years if it earns 9.5% compounded quarterly? So this sort of thing, again, we need to really think about it before we ever address the problem. So let me bring that up because my eyes all go silly when I can't see this. So what's the future value of $8,500? So $8,500 is the present value. So the PV is $8,500. 5.5 years is the length of the loan, so that's 5.5 years. And it earns interest at 9.5% compounded quarterly. Well, compounded quarterly means 4 times a year, so we got to take that 9.5 and divide it by 4. Okay, so let's go. I just got that one worked out. If I can get past thing here. So here's number 2. So the future value is of 8,500 is what we're looking for. 5.5 years, 9.5% compounded quarterly. So in order to be able to figure out what that is, you got to take 9.5 divided by 4. That will come to 2.375%. And it's 5.5 years times 4 times a year because it's quarterly. So in the 22. So we've got this I is 2.375%, 22. So, and all I've done here is drawn a number line. So here's 8,500 and 5.5 years time. This is what we're looking for. We throw that information into the formula here. 8,500 equals 1 plus the I. Now, notice it's 2.375%, but it's in a decimal. We got to divide that by 100 in order to get that into a decimal, which is 0.02375 to the power of 22. So in your calculator, what you do is 1 plus 0.02375. Well, that's easily done. That's 1.02375 to the power of 22. So is that XY on a calculator or a little cap in the computer? And that will give you this. That will work this part out, part that's in the brackets first. Then you multiply that by the 8,500, and that will come to 14,245.74. So effectively what we're saying here is that if we put $8,500 in the bank, it earned 9.5%, that was compounding quarterly, and you left it there for 5.5 years, it would come up to a total of $14,245.74. See how I did that? Well, let's look at number 3. I'll get you guys to do 5 and 7, and so to what amount would 12,100 grow after 3.5 years if it earned 2.5% compounded monthly? So the hardest part of these problems I find is converting the words to the key components that you need to do in order to put it into the formula. So what amount would 12,100 grow? So 12,100 is the base amount. This is the present value. So PV is 12,100. The length of time is 3.25 years. I get caught up in that because I can't see the 4. It looks like 2 to me, old eyes. If it earned 2.5% compounded monthly, so compounded monthly means 12 times a year, so we've got to take that 2.5% and divide it by 12 in order to get the per compound periodic rate. So, and seeing it's compounded quarterly, compounded monthly, that's 12 times a year for 3.25 years. So we got to take 12 times 3.25, and that will give us the total number of compounds. So if you look at number 3 here, so it's the present value is 12,100. The time, 3.25 years, compounded monthly. So we take 3.25, multiply it by 12. That's 39 compounds. The interest rate is 2.5% compounded monthly. So we got to take 2.5% divided by 12, and this gives us 0.21% per month. Now we need to change that to a decimal in order to plug it into the formula. So don't forget to do that. Here's the formula. So the present value is 12,100. 1 plus the I, which is 0.21%, which is 0.0021 in decimal format, to the power of 39. So the first thing we do is we calculate this part right here. So that's 1.0021 to the power of 39. And then we take that and multiply it by 12,100, and that will come to $13,123.04. So effectively what we're saying is $12,100 will grow in 3.5 years to 13,123.04 if it has a 2.5% compounded monthly interest. So 5, assume that a $10,000 investment can earn 3% compounded quarterly. What will be its future value after? So we really got 4 problems in one here, okay? So the present value is $10,000. The rate, the annual rate or the nominal rate is 3%. Compounded quarterly, so that's compounded 4 times a year. So we have to take that 3% and divide it by 4 to give us our periodic interest rate. And then we say, okay, well, if it's compounded quarterly, we got to figure out what is the total number of compounds. So in the case of 15 years, it's 15 times 4. In the case of 25 years, is 25, and so on. So for number 5, basically we've got a present value of $10,000. We've got an I of, well, 3% is the nominal rate. It's quarterly. So what we got to do is take 3%, divide it by 4. That will give 0.75%, which is 0.0075. It's 4 compounds a year because it is quarterly, times the total number of years of the loan in order to calculate the value in. So in the case of A, which is right here, well, it's 15 years. So N is 4 times a year times 15 for a total of 60 compounds. The interest rate 0.0075, that's calculated up here. Plug that into the formula. And so $10,000 will grow to $15,656.81 if that is the scenario, okay? 4 compounds a year for 15 years. In the case of 20 years, same basic information, but what we need is our N changes, right? It's 20 years now times 4, which is a total of 80. So 10,000, 1.0075 to the power of 80. And that comes to a future value of $18,180.44. In the case of C, it's 25 years. And so our total compounds is 4 per year for 25 years, 100. So again, we plug it into the formula. We got 10,000. That should be 10,000 there. I didn't put 10,000. I forgot the 3 zeros. 10,000. 1.0075 to the power of 100. That's a total of 21,110. One of the things you're noticing here is the numbers are going up because the time period is longer, right? In the case of D, for 30 years, well, N is 30 years times 4 compounds a year for a total of 120. We just plug that into the formula, and we'll get 24,513.57. So let's go to number 7 because I'm running out of time. Number 7, we really had a similar situation. What would $10,000 grow to over the course of 25 years, provided we had different scenarios of interest? So our interest rate, or I, is 4%. For relative 4% annually. We got different compounding periods in each one, and the total number of years is 25 times the number of compounding. So in the case of here, A, 4% compounded annually. We take and we're saying, okay, annually, that's 4% divided by 1. And N is 25 years times 1. And $10,000. We just throw those things into that formula. So $10,000, 1.04 to the power of 25 comes to $26,658.38. In the second instance, we had it 4% compounded semi-annually, which is 2 times a year. So we take the interest rate of 4% divided by 2 to give us the periodic interest rate, 2%. Number of compounds, 25 years, 2 per year is a total of 50. Plug that into the formula, we'll get 26,915.88. In the case of C, we've got 4% compounded quarterly. So 4% divided by 4 is 1% per period. 25 times 4, 25 years times 4 periods is 100. Throw that into the formula, we get 27,048. In the case of the final one, D, we got 4% compounded monthly. So we take 4% monthly, take 4 divided by 12, and that will give 0.00033%. The total number of 25 years times 12 is 300. We plug that into the formula, we get 27,134.95.